this week. Our first speaker today is Chen Cheng, who is a final year PhD candidate in statistics from Shanghai Jiao Tong University. Before her PhD program, she completed her bachelor degree in mathematics and applied mathematics from Renmin University of China. Chen's research is about data-driven methods for crowd dynamics modeling with a specific focus on crowd dynamics simulation and the utilization of machine learning and data assimilation techniques to understand and model crowd behaviors. Chen, you may want to start the presentation.
Thank you, Zongren, for the kind introduction. And hello to everyone. I'm here to share my research insights to you. And I'm going to start. Today, I'm going to talk about the data-driven methods for crowd dynamics modeling, which aims to develop more realistic models with the assistance of relevant data to describe the crowd behaviors. Before we dive into the details, let's start with a brief introduction to the context. Crowd dynamics modeling has become increasingly important as our cities experience higher population densities and more large-scale gatherings due to the ongoing urbanization. And these circumstances has led to a rise in crowd-related disasters, such as panic-induced stampedes. So to address these challenges, understanding and modeling pedestrian crowd behaviors has become essential for a wide range of applications. For examples, crowd dynamics modeling can serve as a safe and effective substitutes for traditional evacuation drills. And by simulating crowd behaviors, we can better get the design of public spaces and predict potential danger and thereby saving lives during emergencies. Additionally, when combined with infectious disease models, it can also help study the spread of infectious disease within a population. Given these significant applications, crowd dynamics modeling has attracted attention in multiple disciplines, including physics, social science, and artificial intelligence. And over the past few years, a lot of models have been proposed. Many of these models can be classified as knowledge-driven models, which are built upon experts' knowledge or mechanisms to describe crowd dynamics. And these models can be primarily classified into two types based on the modeling scale, the macroscopic and macroscopic models. Macroscopic models describe the evolution of the crowd's global characteristics, such as density and flow, typically using PDE. And on the other hand, macroscopic models focus on the characteristics of individual particles, such as their positions and velocities, and describe how they move and interact with each other. There are different types of macroscopic models, like the rule-based models, which update positions based on some predefined rules. The velocity-based models, which updates the velocities and then individuals move according to the velocity. The acceleration-based models, also known as force-based models, updates the individual's acceleration, and then it changes its velocity and position according to the acceleration. However, it's important to note that these knowledge-based models often require simplifications and assumptions due to the complexity of the crowd dynamics. While they can provide some valuable insights, they may not fully capture the crowd behaviors. Another category of models that has gained attention in crowd dynamics modeling is the data-driven models. These models do not rely on expert knowledge, but instead they aim to learn mathematical models directly from observed data. It's a useful tool for constructing models that can make accurate predictions of the crowd behaviors. And generally, there are two primary strategies for utilizing data. The first strategy assumes that crowd dynamics follow a specific mathematical model. For example, a certain knowledge-based model mentioned before. However, some or more of the model parameters may be unavailable. And in such cases, these parameters are estimated by fitting the observed data into the model. This strategy is conceptually straightforward and relatively easy to implement, but its performance is ultimately limited by the model adopted. The second strategy, on the other hand, does not impose a specific mathematical model. Instead, the model is learned directly from the data using some machine learning techniques and is often represented by an artificial neural network. This method offers a greater flexibility, but can be more complicated to implement. In this report, I will talk about both types of methods, but I will mainly focus on the second one, and the first one will be briefly summarized after that. Well, first, I'm going to talk about the method of the second data-driven strategy, that is to derive the totally learning-based models. Actually, learning-based methods have attracted attention in the past few years, and most of them are designed to learn models that are discrete in time, which can be used to predict data that are fixed on fixed time intervals, such as the LSTM for long short-term memory and ResNet for residual network. This is mainly because that discrete time models can be naturally formulated with a deep neural network. Like this structure of the ResNet can be applied to learn from data that is observed at time points 1 to capital T. Well, existing discrete time models are convenient to implement and use, but there is strong desire to develop continuous time models. And these models can predict the crowd behaviors at any given time of interest and can provide a more accurate representation of the crowd dynamics. This ability is especially important in emergency situations because continuous time models can provide real-time data and enable immediate response to rapidly changing crowd behaviors. In order to learn continuous time models, we need a continuous time system, and the ODE-Net has proven to be a powerful tool for learning continuous time systems. So our research proposes a method based on the ODE-Net to learn a continuous time model of the crowd dynamics. And let's start by introducing the concepts of the ODE-Net. It's a method proposed by a group of researchers from Toronto University in 2018, which can be used to learn continuous time systems. To understand the ODE-Net, we can examine it from the perspective of a deep neural network. Traditional deep neural networks, such as the residual network, can construct complex transformations by applying a sequence of transformations to a hidden state. This process can be seen as iterative updates, as shown in the upper equation. And here, HZT is a function parameterized by a neural network. This kind of transformation can be interpreted as an Euler discretization of a continuous transformation. Unlike traditional deep neural networks, well, the interval between layers is fixed, typically delta t equals 1. The ODE-Net introduces a continuous version where delta t tends to 0, just like the lower equation shows. Here, the function HZT is also represented by a neural network. In this case, the dynamics are even defined between layers and can change continuously with steps. So this is kind of the core of the ODE-Net architecture and how it differs from the more traditional layer-based structure of the residual network. And let's see how to train the ODE-Net. In fact, the ODE-Net is solving ODE initial value problems. This means that we are given the states at an initial time t0, and the goal is to compute the future states at another time t1. And precisely evaluating this state requires integrating the derivative of the state over time, which is usually done approximately with a numerical solver. Often, adaptive solvers are used for this computation because they can provide error guarantees by adaptive step sizes. With the ODE solver, the ODE-Net is able to output the prediction of the future states, and then by minimizing the loss function between the network prediction and the actual observation, we can update the network parameters theta. We can see that ODE-Net can model the continuous dynamics of a system. Then can we directly use it to model the crowd dynamics? It seems feasible intuitively, like we denote the particle locations and the velocities as x and v respectively, and assume their derivatives are defined by a function capital F. The aim is to learn this function m from data, in other words, to approximate it with a neural network. There seems to be no other difference from the generic setup of the ODE-Net, right? However, when put into practice, directly applying the ODE-Net to crowd dynamics can pose some challenges, primarily due to the crowd size. First, when the crowd size is large, the function capital F becomes high dimensional, and learning this function can be demanding in terms of both training time and the amount of data required. And even if the training is successful, a learned ODE-Net model cannot predict crowds of different sizes, which is different to the training system. For example, we train the ODE-Net with the data from a crowd of 5 particles. It cannot be used to predict the dynamics of larger crowds. Moreover, in some situations, pedestrians may enter or leave the scene of interest. So the crowd size keeps changing, and the ODE-Net cannot describe crowds with varying sizes due to its fixed dimension. So to address these issues, we propose a solution by somehow hybrid modeling, which combines the ODE-Net with some knowledge-based models to embed some known information in the network structure. In some sense, this model provides some prior knowledge of the crowd dynamics. And in order to keep aligned with the continuous structure of the ODE-Net, such models should be also continuous in time. For this post, first model is a natural choice since it's also under the ODE system. Let's take a moment to introduce the social force model, a classic macroscopic model used in crowd dynamics. Initially proposed by Helbing and Moner in 1995, the social force model is heavily based on physics and contains multiple types of forces. Firstly, there is a driving force that adapts pedestrian's velocity to match its desired velocity. For example, in a scenario where a crowd is trying to escape a room, the desired velocity would be directed towards the exit. Secondly, there are interaction forces from other pedestrians. These forces reflect the psychological tendency of pedestrians to keep a social distance from each other to avoid collisions. And when pedestrians come into contact, there are also physical forces coming into play. Similarly, there are interaction forces from obstacles, such as the walls, which prevent collision with them. And all these forces collectively control the movements of the pedestrian. Back to the ODE-Net method. Our goal is to...
Can I ask a question on the model?
Yes.
Yeah, so because the interaction forces, if there's a wall, there's not necessarily a force unless the pedestrian hits the wall. Or is it the influence? I mean, I'm trying to see what you mean by that force. Let's say the last force, which is the constrained by the surroundings, right? Because
the interaction force between obstacles, right?
Right. So there is an implicit force, you mean, right? That will drive the pedestrian the other way, right? So that force has to be there if the proximity to the wall is small, right? That's what you mean.
Yeah, its expression is just similar to the interaction force between pedestrians that consists of psychological force and the physical force.
Right. So that's why you call them psychological force. Physical force is if they bump into each other.
Yeah, when they bump into each other, the forces are called physical force. And when there is a different distance between them, the force is psychologically.
I see. Okay. Please continue. Thank you.
Okay, and I will go on. Now we're back to the ODE-Net method. Our goal is to incorporate the concepts of the social force model to help address the challenges posed by the crowd studies. First, we can incorporate the concept of forces and express the system using Newton's second law, shown in equation 2, instead of a general function capital F on the right. In this equation, the function F represents the forces on each particle, And M represents the mass matrix of particles. It characterizes how easy or difficult to change the velocity of each pedestrian. And now the problem has been transformed into learning the force function F. But at present, this task remains as high dimensional as the original one, which was to learn the function capital F. And to simplify the problem, we need to make further assumptions. Now, we introduce further assumptions to simplify the force function. Instead by the social force that force on each particle consists of a motivational force and an interaction force. And the latter include interactions between pedestrians and interactions between obstacles. And these functions will be approximated by neural networks. The motivational force is assumed to be dependent on the current location and the velocity of particles, while the interaction force depends on relative locations and relative velocities. With these assumptions, the total force function is entirely determined by these three functions. And importantly, they are independent of the process capital N and are of much lower dimensions. For instances, under these assumptions, both FB and FO are four-dimensional. Even with the above assumptions of the social force model, the training is still expensive. So we make further assumptions in our numerical experiments to simplify the training process. Firstly, we assume that the masses of all particles are the same. This simplification is for the application of the learned ODE-Net because we typically do not have information about the mass of each pedestrian, and estimating the mass brings more computation cost. Secondly, we assume that a particle only interacts with its k nearest neighbors. This measure helps reduce the computation cost. And thirdly, we assume that the motivational force depends on its velocity and positions. And lastly, we assume that the interaction force between two particles or the interaction force between a particle and an obstacle depends only on the relative position of the objectives. It means that we remove the dependence on relative velocities. And this assumption is based on the experimental phenomenon that physical forces caused by bumping and body compression are infrequent in particle interactions. And importantly, all these assumptions are made for the computation convenience, and they can be removed or modified if we have enough source of data, and it does not affect the implementation of the method. And based on these assumptions, we arrive at the resulting ODE-Net model. The neural network in this model requires inputs of the current locations X, current velocities V, relative locations of k nearest neighbors, and relative locations of obstacles. And here is the graphical representation of the social force-based ODE-Net. When training the ODE-Net model, the collected data set should be organized in a way such that each data point consists of the crowd state at the initial time t0 and the end time t1. Well, look at this figure. The green module represents the approximated computation of the derivative on the right of the equation, which describes the dynamics of the system. It takes the locations and velocities of all particles in the crowd as inputs, and through a deterministic function Rx, it computes the relative locations of the k nearest neighbors and the relative locations of the obstacles. Then these variables will enter the corresponding network block, and the forces are computed by these parameterized blocks. For example, the relative location enters the block FP, which computes the interaction force in two particles. And all these forces are then summed together. And finally, the initial states along with the approximated derivative function enters an ODE solver, which can compute the predict states at time point T1. And by minimizing this loss function between the network prediction and the observation, and the network parameters can be iteratively updated. For the numerical experiment.
Chen, can I interrupt?
Yes, yeah.
For a second? Could you go back to the previous slide?
Yeah.
So in your loss function, I see you're using this L1 norm. So is there any reason behind that? So in the loss function, you see here, let me annotate here. So why do you prefer this L1 norm over like SA mean square error?
Actually, I have tried the 1 norm and the 2 norm, and it doesn't affect the results. And this 1 norm is taken from the original paper of the ODE-Net. So I just keep it.
You mean the original neural ODE paper?
Yeah, the original ODE network paper uses this 1 norm as the loss function. So I just take it, and it has good results. Also, I tried the loss function with a 2 norm, and the result is very similar.
Okay, thank you.
Yeah. For the numerical experiments, we test in 2 distinct cases to show the performance of a proposed method. In the first case, the training data was generated and collected from the actual social force model. We expect that training on this data sets would be relatively easy due to the similarity between the social force model and the ODE-Net model. And the purpose of this test is to see how the method works when the actual model is similar to the ODE-Net model. And in the second case, the training data was generated from the optimal reciprocal collision avoidance model, which is a velocity-based model and is discrete in time. And I will give more details about it later. In this case, we want to examine the performance of our proposed methods on data sets that is generated from a model that is very different from the ODE-Net model we designed. We first demonstrate the result of the training in the social force model case. And the left figure shows the comparison of particle trajectories in which the solid curves show the trajectories from the actual social force model, which was used as the training data. And the dotted curves represent the trajectories predicted by the learned ODE-Net model. The right figure shows the comparison of the.
Can you tell us before you set up the problem? How big is the N? What's the size of the crowd, and how long is the integration? I see here seconds on the, but how big is the crowd? N. What's
sorry,
what's the
I
capital N?
didn't catch it up.
What's the capital N?
What's the curve of the?
The
No,
size of the crowd.
yeah, the size, the capital N.
Yeah.
How big the crowd is, basically.
Is it 5 people or 100 people?
The training data is generated from the trajectories of a crowd of 5 particles.
5 particles?
Yeah, and the trajectories of 5 particles is used for training.
I see. That's not a crowd. Okay. 5 particles is nothing. It's too small. The size is too small. So
Yeah.
these are the trajectories that you're showing, right?
But I will show later that the training of this model can be used to predict the crowds of a much larger size.
Okay. All right.
Yeah. And the right figure shows the comparison of particles distance to the axis as a function of time, which represents the velocity information of the particles. As we can see, the results of the 2 models agree very well. It indicates that the ODE-Net can effectively learn the crowd behavior of the actual model in this case. We then test the learned ODE-Net model with a crowd of 20 particles, and the results are shown in this figure. Once again, we observe a good agreement between the results of the 2 models, suggesting that the ODE-Net, which is trained with a crowd of 5 particles, can be used to make predictions of a much larger crowd. However, we do observe some discrepancies in certain trajectories near the axis. This is likely due to the physical contacts between pedestrians when they are very close to each other. And such physical contacts are not taken into account in our present social force-based ODE-Net. This video presents a comparison of the escaping process between the actual social force model and the learned ODE-Net, in which 2 are very synchronized. Here, before the second experiment case, let's take a moment to introduce the optimal reciprocal collision avoidance model. As a velocity-based model, the ORCA allows each pedestrian to determine its optimal moving velocities and move accordingly. Briefly speaking, DL defines a velocity obstacle for each particle based on the positions and velocities of laboring pedestrians. It contains velocities that will result in collision with another pedestrian in a certain time interval. Then, for the next step movements, a collision-free velocity is computed by solving a constraint optimization problem that the velocity should be the one that is closest to a pre-described target velocity and is out of any velocity obstacles. With the ORC model described above, we generated the training data sets of trajectories of 5 pedestrians. It's the comparison between the ORC model and the learned ODE-Net model. We can see that the results agree quite well with each other in both figures, but with larger discrepancies than those in the social force model case. But when the model is applied to a crowd of 20 pedestrians and that are closely spaced at the beginning, it's more challenging for the obtained ODE-Net model. we see that the difference between the results of the two models become more substantial than that in the previous case, especially for the distance to the exit, which represents the velocity information. And we believe that the larger discrepancy in this example is due to the fact that the ODE-Net and the ORC model are very different in nature. First, one model is continuous in time and the other is discrete. And moreover, how the interactions between particles take place in the two models is fundamentally different. So we expect that the algorithms can be improved by designing specific network structures according to the ORC model, which is subject to further investigation. And since we have seen the learned ODE-Net model fails in terms of individual behavior in the ORC case, and in many real-world scenarios, accurately predicting the behavior of each single individual is also challenging, and it's often not needed because to model large-scale crowds, it's more important to test the model's ability to predict some important statistical or collective behaviors of the crowd. So we choose two statistical quantities to demonstrate the results. First, we check the instantaneous escape rate, which is defined as the percentage of pedestrians who have successfully escaped the room at a given time, which is N naught divided N, where N naught is the number of escaped pedestrians. Another statistical quantity that we consider is the evacuation time, which is defined as the time for all the pedestrians to leave the room. We can see that although the learned ODE-Net fails in terms of individual behavior in the ORC case, it does capture both statistical characteristics during the escaping process. And the above is the method on the second data-driven strategy. And next, I will briefly talk about the first strategy on data-driven modeling in crowd dynamics. Since in some situations, it's not affordable to develop a totally learning-based model due to the computation cost. And moreover, sometimes the observed data is not suitable for the learning-based method. For example, we may observe the distribution of particles which cannot be used in the ODE-Net method. And instead, in some cases, specifying a suitable model may be good enough to describe the crowd dynamics. So the first strategy on knowledge-based models also has an advantage. Recall that the first strategy is that we assume a specific mathematical model for crowd dynamics, for example, the social force model. And some or even all parameters of the model are unknown, like A and B in this equation of the social force model. Then we will use real-world observations to estimate these parameters, which is usually via a Bayesian framework. That is, we compute the posterior of the parameters given these observations. However, in reality, we often observe the aggregate data that are collected at the ensemble level and do not characterize the state of each individual particle. For example, when the number of pedestrians is large, it's not possible to track and locate each pedestrian. Like in this figure of observation, it's 2 time points. We have no idea where this particle comes from. And instead, it's much easier to observe how the pedestrians are distributed at a given time. But since the relation between the model parameters and the aggregate observations are very complex, it's usually challenging to derive the likelihood function analytically. So in this case, the standard posterior computation methods such as MCMC cannot be used as the likelihood function is not available. And the common practice is to apply ABC methods for this kind of likelihood-free inference. The basic idea of ABC method can be summarized with this illustration. First, we obtain measures of interest from data. This could be macroscopic or macroscopic measures. And then we assume the observation is generated from a specific model and decide on a prior distribution of model parameters. And such as the prior can be assumed to be a uniform distribution. Then we draw n samples, theta 1 to theta n from the prior distribution and use them to perform model simulations. Then a distance function is used to compare the discrepancy between the simulated and the observed measure. And the weight of each sample is defined based on these differences. And the larger the discrepancy is, the smaller the weight is. And finally, we can approximate the posterior with these weighted samples. In our problem of interest, usually the data is observed in a sequential manner. So we choose to base our methods on the sequential Monte Carlo sampler, which is a type of important sampling method. It can generate weighted samples from the posterior distribution, and the sample weights are updated based on the likelihoods of the observation. But when applied in the likelihood-free problems, it requires the ABC method to approximate the likelihoods for computing the weights of samples. So the key issue in this procedure is selecting an appropriate distance measure to characterize the similarity between the simulated and observed data. And for the aggregate observation in our problem, which is the distribution of the particles, most existing methods use the TV distance to measure the discrepancy between two distributions. But it may have some problem in certain situations, which can be shown in this example. We considered these 3 distributions, and in reality, U should be very far from W and be very close to V. But the TV distance between U and V is just the same as that between U and W, which is unable to represent the difference between these 3 distributions. But since the Wasserstein distance means the minimum cost of transforming one distribution into the other, it's more sensible for comparing the difference of this kind of observations. And the Wasserstein distance between U and W is much larger than that between U and V. So we choose the Wasserstein distance as the distance measure in a kernel to approximate the likelihood. Here is the inference results of the parameters in the social force model. The observations are generated from the actual social force model and are used to infer 3 parameters in the model. We can see that the mean values of all 3 parameters converge within 40 sequential observations and are rather close to the ground truth. It indicates good inference accuracy of a proposed method. We have more numerical results, but I will just skip for the time reason. Finally, I will conclude the talk. Today, we present the data-driven methods for crowd dynamics on 2 strategies. One is based on the ODE-Net to directly learn continuous time models of crowd dynamics from data. And we incorporate the social force concept in the network structure to address the challenges induced by the process. This method can be used to learn models for large scale and variable size crowds. And the learned model can be used to make predictions for crowds that are different in size from the training system. And considering the limitations in our method, there are some future works to promote it. First, the assumptions in the network structure is based on the social force concept, which can be modified when fitting data in other scenarios. And second, we can consider more realistic mechanisms, such as the group effect in crowds and the infection of a limited view field for humans. These factors are not taken into account in the present ODE-Net. Second, the second strategy is to assume a specific model for crowd dynamics, and we adopt a likelihood-free sequential Monte Carlo sampler method to infer the unknown parameters from the aggregate observation. In particular, we propose to use the Wasserstein distance to measure the similarity between the observed and the simulated data. And here is some of the references about the 2 researchers. And these are outcomes of my research that have been published or are currently under review. That concludes my talk, and thank you for your attention. I'll be happy to address any questions you may have.
Thank you, Chen, for your presentation. Is there any question?
Yeah, can I ask a 2 questions? The first one is, what was the K, the number of, you said you have a cutoff, so you don't interact, the individual will not interact with everybody in the crowd. So what in the examples you show with, let's say, the 20 subjects in a crowd, what was K, like the cutoff? How many people, what was the interaction range?
Is this figure?
Yeah, remember you talked about if you have a big crowd N and it's very large, then an individual will not interact with everybody else, with just the neighbors.
K nearest neighbors,
yeah,
right?
The K nearest neighbors, right.
Like
in this example,
in our experiments, the K is taken to be 7, and it's borrowed from some references.
7, okay.
We consider 7 nearest particles.
Okay. Is that arbitrary, or you said there's a reference for that, but there's a consensus number?
I think, George, I think she said there's a reference, right? There's a reference. Well, why did
Yeah,
you choose 7, basically?
I didn't put it on, but the reference shows that the number of neighbors to be 5 or 7 would be good for the cross-examination.
Okay. Another question is on when you set up the forces, it seems that you take into account, of course, the proximity to other people and proximity to the walls, but what happens if you have an emergency situation? Like, for example, there's a fire in the building. The crowd dynamics obviously changes. And how do you take that into account through the social force model? Did you hear me? I'm not sure if you hear me or not.
I didn't really catch it. Can you help me explain?
Yeah, George, could you say it again?
Yes. So if there's an emergency situation, so like a fire in the building, how do you take that into account in your social force model?
Yeah,
Because
Chen, did you get
obviously the dynamics changes then.
Yeah, Chen, did you get it? So George was talking about what happened if there's an emergency, such as a fire in the building, or some emergency
Earthquake,
yeah, earthquake, anything else that changes the dynamics. How do you incorporate that effect into your model? So
Well,
the previous slides where you do the modeling, yeah, right. In this slide, how do you incorporate this emergency stuff into this model?
when there is a fire or some like earthquake, this scenario is called the panic-induced stampedes, and the crowd is trying to escape towards the targets, like the exit of the building, and their velocity would be targeted towards the exits. It can probably be described with this social force model, which is designed to describe scenarios for this kind of situations.
So in other words, you don't do anything, just the same model.
We just borrow the concepts of the social force model, but the assumptions can be modified.
Okay.
The aim is not to recover the social force model. It's just for simplify the training of a continuous time model, and the assumptions can be modified as different from the social force model. Like for example, the interaction force can be assumed to be dependent on the relevant velocities and lots of relevant locations at present. Our aim is not to reproduce the social force model. We just borrow the basic concept from it to address the challenges posed by the crowd sizes.
Okay, thank you.
Is there any other question for our speaker?
Hi, Chen. May I have one more question with a neighbor? For a particle, is the key neighbors will change or fixed during the process?
Yeah.
Or if change, how many steps of the training you change the neighbor.
How many steps? What does how many steps mean?
The first question is, did you change the neighbor of one particle during the process?
Yeah.
So you change the every step or how many steps after?
Yeah, how frequent you change the neighbors?
Yeah.
So for every time step you update for a particular particle, you update its neighbors every step, every 10 steps or every.
Did you calculate the distance of each particles every step?
This actually the relative locations of the neighbors is computed every step when use the network.
Okay, so
Okay,
you average.
thank you.
Yeah.
Okay. Thank you.
Okay.
Is there any other question? No? All right. Thank you, Chen, for your presentation, and thank you for staying up late. Yeah, we'll move on to our second talk, and you're welcome to stay here for the second talk. Yeah, thank you.
Thank you, Zongren, for your help, and I will leave the room.
Yeah,
Bye
sure.
bye.
Bye. All right, now let's move to our second talk. Our second speaker is Dr. Thomas Torku. Dr. Torku obtained his PhD from Middle Tennessee State University in May 2023, and his research focused on data-driven models in computational and data science. Dr. Torku is particularly interested in disease modeling, including epidemic models, stochastic modeling, quantitative analysis, big data analysis, and cloud computing. He will be talking to us about his PhD dissertation. Oh, I see. Hello?
Hello.
Oh,
Sorry.
now I can hear you.
Sorry. Good afternoon from here, and I'd like to appreciate Professor George for this opportunity. A quick background: I joined this crunch group in 2020 when COVID was at the peak. Before then, we were exposed to PINN, and it's been a great resource and a tool to us in our research group to be able to explore PINN and see the applications that we can have. The main takeaway of this talk is the application, because a lot of deep neural networks have been applied and machine learning tools have been applied to COVID-19. But my focus today in this talk is to highlight the importance of PINN and the variations our group came up with to learn various aspects of different types of epidemic models. Thanks to Esson and the paper they published also on COVID-19, we were able to also extend it to pretty cool models. This is the overview of my talk. I'll briefly introduce some key tools that was used in my dissertation, the challenges of deep neural networks, data-driven simulations, go through the pre-processing stage, why cross-validation, and the essence of error metrics in analyzing data-driven simulations. These will be applied to these three models: the deterministic model, a stochastic model, and I'll explain why stochastic models are also important. And we compared stochastic model with deterministic model, and our results show that stochastic models are better when we have high noise within the data. Behavioral models are very important also because most models we see ignore the essence of social interaction or ignore the essence of human factor, the behavioral factor that affects the dynamics of COVID-19. And then I'll wrap up with the conclusion. So the first question is, why deep learning for differential equations? And pretty much everybody on this call has some basis or background in differential equations. And we know that when the dimension of the equation becomes large, we have the problem of chaos of dimensionality. And with the advent of deep learning, we're able to solve that kind of problem. And then with time-dependent parameterized models, it's been shown in literature that deep learning learns those time-dependent parameters very well. And then inverse and forward problems as well. In particular, when we have integrate structures in high-dimensional data, deep learning has proven also to effectively learn those structures. And then looking at complex dynamical systems and large scale prediction, deep learning does well. And of course, high-dimensional partial differential equation. In the next couple of slides, I will walk us through a couple of traditional neural network frameworks that we used in my work. First, the feed-forward neural network. We all know it goes from the input to the output. We have the input layer, the hidden layer, and the output layer, where the input data goes to the hidden layer, where we have some activation function applied to sort of put the data within a framework that will help the neural network to process it until the output layer. And then we get a target, we compare it to the actual data. There's some sort of optimization that goes on, and then we're able to do our prediction. The residual neural network, we also use that, and I'm going to tell us why we use that in our work as well. Basically, is the first forward Euler method, and the structure allows for some sort of skip connection where that residual neural network is able to avoid the problem of degradation in the performance of the model when we have large number of layers within the architecture. We also employed sequential model. When I say sequential model, I mean the time series. Whenever we're dealing with time series, then we need to use recurrent neural networks, and we also use recurrent neural networks and the variant of recurrent neural networks. We have the long short-term memory, the LSTM, which solves the vanilla RNN problem of vanishing gradient problem, and then it has this gates, which also helps it to process the data. The bar-LSTM also is a variant of the RNN, but it has the forward and backward propagation that allows for also improvement in the traditional LSTM. But the drawback with this is that computationally, because of the forward and backward propagation, it requires long time. The gated recurrent neural network, on the other hand, is an improvement of the LSTM as well. It reduces the number of parameters. We saw from the previous slides that the LSTM has a number of parameters. And so when we have the gated recurrent neural network, the input and forward gates are merged into update gate. And that means the number of parameters that the architecture learns will be reduced. Hence, the gated recurrent neural network happens to improve the overall performance, and also in terms of time, the computational time, the GRU works better. What are the challenges of deep neural networks? And here we have the loss function. What is the right choice of loss function that we need to make? Optimization technique, quite a number of them. And also the learning rate. The learning rate shows the strength of the connections between your neurons as they change over time. Then the right choice of activation function. These challenges are what makes neural network interesting and also challenging. That the right choice and the right choice of these hyperparameters will help to produce the target and also the goal that we set at the beginning of the modeling process. Data-driven simulations. So first, we'll quickly explain to us some techniques in the data-driven processing and then why the need for cross-validation and error metrics. In data pre-processing, there are 4 main steps. We have the data cleaning phase, we have the data integration, data specification, data transformation. In the data cleaning, we tend to handle all the missing values and anything that is missing within the data, we impute them. For example, if as and when COVID-19 began and the data was missing, there was a need for us to handle that. And then also with data integration, where data is integrated into folders. For example, when COVID-19 began, John Hopkins team created a folder in GitHub where everybody could access that. And then data specification, if we're interested in the death column, the recovered column, the infected column, then we specify what we want. And then with data transformation, you transform the data into the form that you want it to be. That way, the neural network is able to learn what you want it to learn. Some of these techniques are useful. The left censoring, the right censoring. The left censoring has to do with when at the beginning of your data collection process, the data you have is inadequate. And so how do you handle that? At the beginning of COVID, what happens is that many countries did not have complete record of data. And so as a modeler, you need to decide which data you are going to start from. So that's the left censoring. The right censoring is after a time when the dynamics of COVID was ongoing, or the evolution of COVID was ongoing, there was vaccination came in, other variants of COVID-19 came in like Delta, Omicron, and everything. Right censoring implies that we need to account for all those new variables that have come in. And then of course, Z-score and minima scaling are not new to us. Cross-validation. After we've done data-driven simulation, there's the need for us to evaluate the models, especially if you are dealing with several models. One of the ways to do that is to apply cross-validation or do error metrics. With cross-validation, one could do random splitting to start with, where we split the data according to chunks and to folders, and then we partition that, and then depending on the folders you choose, one of them will be used as a test set to score that performance or the predictive outcome from that test set, and then we take the average of those scores to be able to compare 2 or 3 or 4 or more models together. Error metrics. Basically, one of the contribution of my dissertation is to pinpoint all the various error metrics that can help modelers to, as it were, use these metrics to be able to compare models, the performance of models. We have the absolute errors, we have the log errors, you have the squared errors, you have the correlation errors. I'll talk a little bit about the correlation errors because we are dealing more with the regression stuff. So we have the RMSE, which is the root mean squared error. We have the MAPE, which is mean absolute percentage error. The relative error, of course, in the mean absolute error. and then they explain variance as well, which is analogous to the coefficient of determination in a linear model. In particular, though, the relative error also measures sort of a percentage, measures the difference between the predicted and the actual values expressed as a fraction of the actual data. And then the concordance correlation coefficient is useful for those researches done in health-related form that is applied to health-related data. This metric, even though was not used in my research, is there to help any reader to appreciate how these error metrics can be applied to health-related work. Now, for the next slides, I'll talk about the 3 models we considered and also touch on the variant of PINN that we came up with. We have the epidemiology-informed neural network, the stochastic epidemiology-informed neural network, the behavioral epidemiology-informed neural network. First, we considered a deterministic COVID-19 model where we assume there's no noise within the model. Now, with this basic SIR model, the parameters that we wanted, PINN or EINN, here EINN, because it's a variation from PINN, is the transmission rate and the recovery rate with fixed vaccination rate, as well as its efficacy. And the goal was to confirm a well-known fact that when you increase the vaccination rate per time, you would notice that the infectiousness, the rate of infectiousness also reduces. That was the goal. This is the overview, a simple schematic diagram explaining how we learn that. We have the input layer and the hidden layers, and then we encode the SIR model, and then as well as the infected data, and also the available data we have with the initial values. And then we learn these beta and gamma so that we can calculate the basic reproduction number. And this was at the initial stages of COVID-19 before vaccination was rolled out. And so this is how the loss in the EINN works. We have the residual in the data, the differential equations, which actually encodes the epidemiology of the model, as well as the initial conditions. Now, in terms of the algorithm, we set the input argument, we construct and run the neural network by specifying the weights and the biases, as well as the activation. The activation function we use over here is hyperbolic tangent function. And then we computed the residual function, the residuals, then encoded epidemiology. Now, in the next slide, I will show you how we observe, as we learn different beta and gamma, the impact on with different choice of vaccination rate. So as we can see on the right side, we see that as the vaccination rate begins to increase from 5% to 1% to 2%, 3%, we also see that the basic reproduction number decreases correspondingly, as well as the level of infectiousness also decrease accordingly. The day it peaks as well, the day of peak of also decrease correspondingly. Now, this is where—
Thomas, can I ask you a question? Because I thought the beta and gamma in your models are constant, but here they varied. Are they variables? Are they a function of time?
In this context, we didn't make it a function of time. We just made it constant.
But here, as the vaccination rate changes, which is of course as time changes, the vaccination rate will change during different periods. Then these constants are not constant.
They are not constant in the model itself, but we are looking at it for 10 months, as in the last day of the 10 months, we see this is what we learn.
Oh, so in the model is variable. I'm still confused. The model, in the model, when you're trying to find, because you do parameter estimation, are
Yes.
these parameters constant in time or varying in time?
Yeah, they are constant in time at the end of the 10th month. We wanted to do the time-dependent variable, the time-dependent version, but because this was already published, it was a recommendation that was made by somebody else, but it's part of it could be part of the future work to do, but we only consider this as a constant parameter.
So excuse me, but in the model that you consider,
Yes.
also vaccination rate is constant. So here, if we vary the numbers, we're varying model every time, right?
Right.
You're different scenarios.
Yes.
Okay. Thank you.
Yeah. Professor George, is it clear?
Right. So it's piecewise constant, let's say.
Yes. Per time.
And you choose those periods of yeah. Okay.
All right. Thank
Yeah.
you. Okay. And then the next thing we consider is what we call the hybrid approach. The idea of the hybrid approach was to say, hey, can we look at one architecture smoothing out the noise in the data and using that to predict the next. So that's the idea of the hybrid approach. We combine ResNet with variant of recurrent neural network, LSTM by LSTM and Guru. So what we observed was that the Guru, as I explained in the intro, Guru tend to perform better in terms of speed and accuracy as well. As we can see on the next slide, the error metrics show that by ResNet Guru, in terms of the error metrics, was giving us a better learning ability. And then also graphically, we show that with RMSE and MAPE, we observe that ResNet Guru was giving us better learning ability. We also apply the cross-validation to be double sure of our assertion that ResNet Guru was better. And we can see by choosing different folds, we have the K equals 4, K equals 5, K equals 6, K equals 7. We observe that indeed ResNet Guru was doing better. And we did a little bit of prediction 15 days into the future prediction. Now the stochastic COVID-19 vaccine model. Now the idea of this model was to say, at a point we saw that there was a war going on. What is the effect of external factors such as war or the mobility of humans across states, across regions, across different nations, and the impact on the model? Hence, we have the stochastic model, where the sigma 1, sigma 2, sigma 3 represents some noise level within the model, and as well as the W1, W2, the Brownian motion. And again, as we increase the intensity of the fluctuation of the noise or the noise, we wanted to observe the impact of the model. Now, we've submitted this paper for publication and it's under review. In this paper also, we considered model with nonlinear incidence rate, and I'll talk about the significance of the nonlinear incidence rate as well. This is the model that captures the dynamics of what we call the nonlinear incidence rate, represented by a function of G of the susceptible group as well as the infected group. All these parameters, we kept it constant for reproducibility. If somebody wants to reproduce our work, our goal was to see the impact of varying sigma 1, sigma 2, sigma 3 in the model. Here, when I say varying the sigma, I mean sigma 1, sigma 2, sigma 3 is kept at the same value, but then varying it for different scenarios. What is the impact on the overall model? So the GS is basically the nonlinear incidence rate. It's with some parameters as K being the proportionality constant and H being some positive numbers. Alpha measures the psychological effect. So we kept that. Since we know the infected group, we can easily find the substitute. Since we know the infected group and the recovered group, we can easily find the substitute group as well if we know the population size. So in this paper, these parameter values were kept constant, the H, the K, and the choice of alpha. Of course, these values were chosen from a published paper. And then we considered only two vaccination scenarios, 1% and 10% when it's high, and different levels of noise. We perturb the data with 5% noise, with 10% noise, with 20% noise, with 60% noise. I want to see the impact on the GIs as well. As I said earlier on, BD, gamma, and these parameters were assumed fixed within the model.
Hey,
yeah.
excuse me, can I ask a question? This is Adar from Brown. What does it mean noise? Like, what's the physical meaning of noise in this case?
Yeah, that's a good question. So the noise here we're talking about is the external factors. So it could be the war in Ukraine. It could be any other thing other than the what is happening with the COVID. Like for example, a classical example is the war in Ukraine. Any external factor.
Yeah, I understand, but like, how does it alter the dynamical system? Like, there's a war in Ukraine, but you're also looking at like COVID.
Yeah,
recoveries, right?
Yeah, so what I mean is, for example, when there was a war in Ukraine, we found people being evacuated to the US and other places. So, I mean, that was when even the COVID-19 was dying down. But more importantly, if there's a noise vis-a-vis COVID-19 spread, the mobility of people around the globe is also going to impact if necessary public health measures are not taken in place. Does that make sense?
So I understand. So like mobility, the mobility parameter is altered. Okay, gotcha. Thank you.
I think the way to understand it's more like uncertainty.
Yes.
That you're not committed to one, but basically you create a band of answers, and within that, so yeah, so it's not. I mean, it's not directly interpretable, I think, but it does allow flexibility, and then of course the sigma 1, sigma 2, sigma 3 are learnable parameters, so that from the fluctuations you can see this uncertainty band.
Yeah, thank you, Professor George. That's well noted. What we did with this stochastic epidemiology informed neuron, which we call the SEINN, was to specify the sigma 1, sigma 2, sigma 3, 5%, we kept them the same. And then we sort of did some Monte Carlo where we loop through by specifying the using the Euler-Mariamma discretization. And then if we specify the number m, we'll loop through all of them, and then we find the mean squared error for that. After finding the mean squared error, and then we average the loss from there, and then we add it to the loss coming from the data itself. So we have the loss from the data itself, and then the loss from the residual, which we're calling the Monte Carlo the Monte Carlo Euler-Mariamma discretization form. And so once we do that, the loss, and then through optimization using TensorFlow, we're able to learn these parameters. But the goal here was not basically learning the parameters. The goal was to see how we can fix the data as the percentage. So we kept all the parameters fixed, and the goal was to really learn them, fit the data in this noisy sort of data environment. And we chose the data frame from December 17, 2020 to May 16, 2020, just 3 months of data. And what we did was to interpolate, because we know physics-informed neural networks are data hungry. So we interpolated with some 3,000 data points to learn the dynamics when we have 5% noise. And so we did some comparison in terms of the deterministic, it was very terrible, but in terms of the stochastic, it was able to relatively learn the form better. That's 5% noisy data. And then with 60% noisy data, both of them failed woefully, but stochastic epidemiology informed neural network landed better. And this is where we have a future work. I'm considering the Bayesian approach, either GAN or Bayesian approach, to see if we can really fit the data well in the presence of high level noise. We can see from this.
Excuse me. Can
Yeah.
I ask a quick question here? This
Yes.
is Panos from Pacific Northwest National Lab.
Okay.
When you say, for example, 5% noise or 60%, what
Okay.
is this percent with respect to what?
To the data itself. So I just randomize. So we have the actual data, right? And then we
I see.
Yeah, then we perturb it with 5% random noise.
But okay, so this is not the sigma 1, sigma 2, and sigma. This is just for the data itself.
Yeah, this is for the data itself, but within the model itself, we kept sigma 1, sigma 2 at 5% for all of them.
When you say 5% for sigma 1, what do you mean 5%? I mean, sigma 1 is a number, right? So
yeah, it says sigma 1, sigma 2, sigma 3. Sigma 1 equals sigma 2 equals sigma 3 equals 0.05. 0.05, I mean.
okay, so
Yeah.
there are, in other words, you have noise on the data, but you also have in the model the same noise.
Yes.
Somehow. Okay.
Yes.
So do they have to be the same?
Not necessary, and that's why this opens up to so many work to do. We can look at it being different. We can look at it being the same. But for this paper and this work, we look at it being the same.
Okay, and what you call deterministic here is when you set the noise to 0, right? And you try to fit the data.
Correct.
Okay, great. Okay, thank you.
You're welcome. And so we observed that the SINN did a pretty not so good work, but did better in comparison to the deterministic. And it's obvious with the error metrics, with the RMSE, the MAPE, we see eventually that as we increase the noise level, 5% to 10%, 30% to 60%, we observe that relatively stochastic model was, the stochastic epidemiology neural network was doing better in comparison to, in terms of the data fitting. The next was the model with the nonlinear incidence rate. So per the function we saw for the GSI, we observe that if it's 5% again, the GSI will put to pretty fitted better, but when it's with 1% vaccination rate. So here also we're looking at the interplay of lower noise and lower vaccination rate. But on the next graph, we have higher noise with higher vaccination rate, and still we observe that the SEINN can be better. And that's why in the future work, we'll be considering Bayesian approach and see if we can really fit the data very well in the presence of high noise. All right, the behavioral COVID-19 model. The motivation of this model was basically by National Science Foundation. They were curious to know, are there social interactions, behavioral patterns that really are being excluded from present existing models that do not capture the effect and the impact of social and behavioral effect. And so our model was inspired by that. Basically, we have what we call a time-dependent behavioral parameter. And so in this case, we considered everything as a time-dependent model, where the transmission rate was a time-dependent model. The recovery rate was also a time-dependent model. And then the death rate was just also a time-dependent parameter. But here the idea is compliance rate. So the CT here at the extreme, if it's 0, it means no people did not comply to mitigation measures like wearing of masks, not wearing masks, like going to take your vaccine or not going to take your vaccine. And then if it's 1 or 100%, then so we had this bound of 0 to 1 or 0 to 100%. If it's 100%, then everybody complied, but which we know realistically that is highly impossible in the real world sense. So we learn something in between. So we have 1 minus those who comply. So this is an updated model where we incorporated explicitly a time-dependent behavioral parameter. And so in terms of the effective, because this is time-dependent, we have effective reproduction number will be defined in this context where we have the death rate as also a time-dependent parameter. And then the updated transmission rate will be there. So the idea of this paper was to see the impact of the behavioral parameter on the reproduction number and as well as the transmission rate, and also other parameters within the model. But we focus on these 2 key epidemiological parameters. So here we sort of introduce some regularization parameter to also improve the predictive performance, as well as some sort of attention mechanism. We're trying to see whether attention mechanism can also help in the presence of noise, although we didn't include noise in this particular work, which can also be a future work to consider. So the new thing here is the regularization parameter, epsilon, as well as some sort of attention mechanism. And then the loss here, we penalize, we give a higher weight to the loss coming from the data, and then a lower weight to the loss coming from the residual. So everything else remains the same. And this is the outcome we obtained. First and foremost, we compared a normal PINN with BEINN, and it's expected that PINN and BINN will give us different dynamics of the compliance rate. So the compliance rate means that, from December, from the time we chose, which is March 30th to December 16th, at the time when vaccination wasn't in play, we observed that we learned different dynamics of the compliance rate. We see that more people are complying. That was in Tennessee. This is basically for Tennessee. And then for New York, also, we observed that more people began to comply with the mitigation measures, wearing of masks, not wearing of masks, as well as Michigan as well. But the difference we observe is the impact that each of them had, but we're focusing on the BINN. So the blue curve here is the learned transmission rate. And then, so we observe that as more people complied, we observe that the transmission rate begins to fall. And this is consistent with what we should expect when more people, holding all other factors constant, when more people begin to comply to mitigation policies and measures, we should expect the transmission rate to fall. Same for New York as well as Michigan. And also with the effective reproduction number. Yeah, okay.
So you have an extra networks, right? So beta T is represented by network, right?
Yes.
And gamma T, all these are now represented by networks, like
perfect.
In addition to pins and bin, right?
Yes, sir.
Okay.
Great. Now, With the effective reproduction number, we clearly see also that that the impact is reasonable and consistent with what we should expect. That although at the earlier stages of COVID-19, some of these states like New York, for example, there's so much going on at the early stages of, but what we should expect is being shown here, that relatively there is some sort of volatility, but overall, the pattern shows that as we increase in the compliance, we also see the impact that it comes down. Same for Michigan as well. And then we try to do some data fitting just to compare, although pretty much by eyeballing, we can see that they pretty much fitted very well, but there was some sort of good performance coming from the BINN, and we compare the CPU time analysis of that as well. RMSE was doing better for BINN for Tennessee, as well as for New York, and also for Michigan as well. And this can be extended to other countries, other states in particular. The last part of this talk is just sort of computational analysis, which I'll call the sensitivity analysis of the architecture. We just wanted to see if the neural network is a little stable. We increased the neurons from 32 to 64. I wanted to see also varying the regularization parameter. Want to see how stable the BINN was. And in terms of these analysis, the goal is to inform the modeler that these sensitivity analysis helps you to make the right choices of number of parameters with regard to the neurons and other parameters of the model. And then in terms of overfitting, we did divide the data into 80%, 20%, the train and the validation loss or the test loss. It proves that after 10,000 epoch or 20,000 epochs, we observe for 40,000 epochs, we observe that the test and the train loss are the same. Also, as more epochs are added, we observe that the overfitting is taken care of as we increase the regularization parameter. And then for this table just gives us an overview of some just varying number of layers as well as varying different neurons, the corresponding RMSE and the error metrics in general. And some computational time analysis of the regularization parameter implies that here, if the regularization parameter decreases, we observe that with increased neurons, the number of time, and it's expected the number of CPU time will be lesser compared to more neurons. So in summary, before I give the conclusion, I would like to say that the PINN have really been inspirational to our work. So I provided the tools in the background needed to do data-driven simulation. We summarize the effect of increased vaccination rates in reducing the level of infectiousness, and demonstrated the significance of stochastic models with varying noise levels for nonlinear incidence rate. We showed the impact of behavioral and social factors on the spread of COVID-19. And then the future work which we're considering is the use of spatial and temporal epidemic models to capture the spatial component like the mobility of humans, include more and more social and behavioral parameters, because that is what National Science Foundation are interested in right now, that they want to really get it right before any future occurrence of any pandemic. And then, of course, behavioral effect of maxing and non-maxing, and then doing Bayesian for stochastic models. Before George says anything, I would like to say that right now, as I'm done with my PhD, when hiring managers talk to me, I'm like an ambassador. I'm selling PINN to people, like they are so interested, and so they like the concept. PINN as I talk about my work. Thank you.
Thank you for your presentation.
Thank you.
Thomas, I just wanted to congratulate you. I think that's an excellent thesis, so I wish you good luck with your job.
Thank you so much.
Do you have questions for Thomas?
I ask one question. This is Hassan.
Hassan, please go ahead.
So when you have the stochastic model, is it possible to also get the uncertainty bound over the estimation that you have?
Yes, I think that's a good point. That'll be future work actually, because if we consider the Bayesian and other stuff, we could do that as well. Yeah.
Yeah, that would be interesting to see when you have like 5% or 60% noise. How
Yes.
much of the uncertainty bound you have over the estimation. And one more thing was, this is what we looked into more carefully when we're dealing the paper, the forecast of the model that you have.
Right.
Sometimes we see that during the training, it actually performs very well, no matter what epidemiological model we adopt. But they perform completely different when you do forecast. So maybe something that you can look into for like the stochastic model, especially if you have the uncertainty bound, that how the forecast in time, the uncertainty bound is gonna change and grow in time with the different models that you have.
Yeah, thank you. I will do that.
Hey, again, this is Adar. Not much of a question, but more of a small comment. So regarding the stochastic, the noisy model,
Yeah.
you might want to look into diffusion models because they might really help here.
All right, thank you.
Learning incremental noise like yells to me diffusion.
Thank you so much. Yeah, we'll look into that.
Any more questions, comments from the audience? No? All right, thank you, Thomas, for your presentation. Thank you for attending our crown seminar.
Thank you.
And right, so it comes to an end to this week's seminar. Everyone has a good weekend ahead, and I'll see you next week.
Thank you.
Bye.
Bye.